In this lesson, we will talk about concavity. Now, concavity is a little bit different from the concept of increasing and decreasing. Here's our official definition. If we talk about concave up, what that means is the derivative is increasing. The best way to describe it is, let me go ahead and go straight to the example. What we do is we think about some of our tangent lines. What I'm going to do is just draw in a few little tangent lines on the graph, like what we've been talking about for our derivatives. These little tangent lines represent the slope of the graph at a single point, and these are the values of the derivative, the slopes of these things. As you go along this graph, notice that these slopes are very positive, a little less positive, a little less positive, 0, then they get negative, a little more negative, but then they start getting a little less negative. There's a 0 in here, and then it becomes positive, and more positive, and more positive. We can think about these as slopes and say, when are the slopes increasing, and when are the slopes decreasing? That's the idea of concave up and concave down. If you look at where I described that the slopes were increasing, it was starting around 0. Around 0, the slopes began to get less negative. Remember, a less negative number is higher than the original. Then it became 0, which is higher than any negative number. Then it became positive. And then it became more positive and more positive. So from 0 onto infinity, this function has increasing slopes. That's what it means for concave up. I'll give you another definition. Notice that from right here, the graph appears to be bending upward. Bending upward is also an idea of concave up. For this particular example, it is happening on to infinity. This is an interval. Now concave down, it's the same idea, but when the slopes are decreasing. And also you could think of it as bending downward. That happens all the way up until about 0. You'll notice the very positive slope becomes less positive, 0, negative, more negative. These values are decreasing. Therefore, concave down is on negative infinity to 0. Here's how we're going to calculate these things. What it turns out is that what we did for increasing and decreasing by using f prime, we'll do exactly the same thing with f double prime for concave up and concave down. The second derivative is just the derivative of the derivative. What it turns out is that when the second derivative is positive, the function's concave up. Remember, when the first derivative was positive, that meant the function was increasing. Second derivative negative means concave down. And second derivative 0 is something we'll talk about. So recall, before we said when the first derivative is 0 or undefined, we got some critical values, we tested them, and we found increasing, decreasing. What we're going to do similarly is to find these things, we're going to find what we sometimes call hypercritical numbers. The critical numbers, but for the second derivative. It's where the second derivative is 0 or undefined. We do exactly the same process, but with the second derivative instead of the first. We find where it's 0 or undefined, put it on a number line, and find test intervals. Choose some test points. And what we do is now the test points go into the second derivative. We're going to test for concavity with the second derivative. If it's positive, we have concave up. If it's negative, we have concave down. Next is what's called an inflection point. Recall that we had the idea of a relative max and a relative min whenever the things switch from increasing to decreasing or from decreasing to increasing. We do have a similar idea of when the concavity switches, but instead of two different ones, if the concavity ever switches at any point on the graph, we call that an inflection point. You do not have to pay attention to whether it switches from concave up to down or concave down to up. Just if it switches at a point on the graph, we call it an inflection point. If we're going to find an inflection point, it's going to happen at one of these, as I called, hypercritical numbers. So it's going to be a very similar circumstance. We find where it's concave up and concave down, and we draw a picture on the number line. If it switches, that's an inflection point. Let's do our first example. We've got f of x equals x squared minus 4x, and you might notice that these are going to parallel nicely with the previous section. in that I'm using the same examples. This time we're doing concave up and concave down. We need to take the second derivative. The first derivative is 2x minus 4. And so the second derivative is the derivative of the derivative. I take the derivative of 2x minus 4, and I get just 2. If we try to draw our number line, we have an issue here. The second derivative is 2. If I try to set 2 equal to 0, I get no solution. It's never undefined. What it just boils down to is there are no hypercritical points at all. So my number line is going to have nothing on it. Now this might be a bit of a strange looking example, but we'll do another one also. I've got nothing on it. Well, let me just pick a test point. I'll just pick 0. And I'm going to check that test point, this time in the second derivative. Well, my second derivative is 2. So when I plug in 0, there's nothing to plug it into. I still get 2. That's positive. And so often what we do when it's positive is we draw concave up kind of like a parabola. It's positive, so it's concave up. We can go ahead and write an answer for this. Concave up is on negative infinity to infinity. Concave down, none. The inflection point, well, the inflection points would occur at your hypercritical points. We didn't have any, so there's also none of these. This particular one is rather boring because it's just concave up everywhere. But let me take you back and point out some stuff we found previously. I'm just going to give you some of the information before. What we found before was that this function had no relative max and had a relative min at 2, negative 4. And we found that the function was increasing on 2 to infinity and decreasing on negative infinity to 2. I'm getting the shape of the graph. You'll notice this graph is bending upward, bending upward, bending upward all the way. Gets to 0 and it continues to bend upward. With that said, very negative slopes become less negative, become less negative, become less negative, hit 0, then they become positive, and more positive. The slopes are increasing the entire time, which is why this thing is concave up on its entire domain. This one I need to take the second derivative, so I'll first calculate the first derivative. I get 6x squared plus 6x minus 12. And then the second derivative, I get 12x plus 6. Now that I can actually get a solution if I set it equal to 0. So if I set it equal to 0, I get 12x equals negative 6, so x equals negative 1/2. Good, now we can do something. So let's plot our number line and put negative 1/2. And by the way, notice that the second derivative is always defined. There's no places where it's undefined here. So at negative 1/2, I'll choose a test point. 0 is to the right of negative 1/2, and negative 1 is to the left, so I'll use those points. And again, for the concavity, we plug it into the second derivative. So at negative 1, I get 12 times negative 1 plus 6 is negative 6. And at 0, I get 12 times 0 plus 6, which is positive 6. At negative 1, it's concave down. Again, I usually draw that like this. And at 0, it's positive, so it's concave up, which I usually draw like this. So let's answer the question. Concave up is from negative 1/2 to infinity. Again, your test points are not part of the answer. Concave down is negative infinity to negative 1/2. Inflection point happens at, remember these are points, negative 1/2, but I need a y value. I don't have a y value. What I'm going to do to find the y value, I'm going to plug it back in to the original function. Just like when we did local max and local min, we plugged it into the original function to find the y values. We also do that for the y values of the inflection point. I get 2 times negative 1/2 cubed plus 3 times negative 1/2 squared minus 12 times negative 1/2. A little bit difficult arithmetic, but feel free to use your calculator if you want. I get 13/2 for my answer. There's our final answer. And again, just because I want to show you guys how this works together, let me draw you a graph. Using the information from this same problem, we found that this function was increasing from -infinity to -2, and also from 1 to infinity, and was decreasing between -2 and 1. The max was at -220, so I'll go by tens here, and the min was at 1, -7. If I draw -220 and 1, -7, what we just found was an inflection point at -1/2 13/2, which should be 6.5. So something like this is an inflection point. We found that it was increasing previously and then decreasing here and then increasing again after. Now notice the way that I drew this, and this is the proper way, it does appear that it's bending downward, but then right around where this inflection point is where the concavity switches, and it begins to bend upward, and upward forever. So these are the graphs that come up. For this last example, let's just do this one without any graph. We'll start off by taking the second derivative, which means we first need to take the first derivative. So if I take the first derivative, I'm looking at a chain rule problem. I'm going to take the derivative of the outside, which is the e function, and then multiply it by the derivative of the inside, which is the exponent. Simplifying, I get e to the -x² / 2 times, this will become a -2x/2, which is just a -x. To take the second derivative, I'm going to need the product rule. So for my product, I'll have this is my first, and this is my second. And notice I'm taking the derivative of the same thing I did before, so I'm going to shortcut that just a little bit whenever I take my derivatives. For the product rule, you have the derivative of the first times the second plus the derivative of the second times the first. This first one, I just took his derivative and got e to the -x² / 2 times -x. I have another -x. Then the derivative of -x is -1, and I again have the e to the -x² / 2. I'm going to set this equal to 0, and when I do, I'm going to go ahead and do a little simplification. Let's take the e to the -x² / 2 and factor it out. What's left is a -x times -x, which is x², and the -1. And that's what I'm setting equal to 0. However, this part is never 0. Since it's never 0, I really can just take the x² - 1 equal to 0. You can solve that by factoring or square root. I think I'll choose square root. I get x² = 1, so when I take the square root, remember to do a plus or minus, and I get plus or -1 for my hypercritical points. Let's put that on a number line, -1 to 1, and then as usual, pick our test points. I'll choose -2, 0, and 2. And just like the previous examples, we need to plug those into the second derivative to see where they are positive or negative. Now I'm going to take a little shortcut this time. The e to the -x² / 2 is always positive, so it's not really going to have much bearing on whether the second derivative is positive or negative. So what I can really look at is just the x² - 1. No, this is not the full second derivative, but I'm just going to take a little shortcut. The full second derivative would be h double prime of -2, so I get something along the lines of -2², which is 4, and 4 - 1 is 3. So 3 is positive. I have 3 times some number that's also positive. So rather than calculate this directly, let's just grab what I really want to know. It's positive. And then I'll take h double prime of 0. When I plug 0 into this, I get x² - 1, so x² is 0, 0 - 1 is -1, Again, times something positive gives me a negative number. And then when I plug in 2, I'm going to get a very similar answer to when I plugged in negative 2, which is also positive. So that gives me concave up, then concave down, then concave up again. For concave up, that will be the regions where the second derivative was positive. So I'm going to have from negative infinity to negative 1, I had concave up. And also from 1 to infinity, I have my concave up. And then for my concave down, that occurs on negative 1 to 1. Finally, the inflection points. You'll notice that inflection points on this one will happen at both negative 1 and positive 1, because that's where the function changes concavity. I'll need to find the y-coordinates for these also. So I'm just going to say they're at negative 1 with an unknown y-coordinate, we'll put it in a moment, and also at positive 1 with some unknown y-coordinate for us to find. Remember, to find the y-coordinates, you will plug them into the function. H of negative 1 is e to the negative 1 squared over 2. I'm just going to keep that right as it is. That is an e to the negative 1/2. So that will be my y-coordinate. And then for h of positive 1, you might already see this won't be any different. I just get a positive 1 squared, which is the same answer. I again get e to the negative 1/2. And those are my inflection points, as well as my concavity. One final thought for this lesson is the second derivative test. This is just something that is helpful in some of the problems we may encounter in the future. Right now it doesn't really give us a great deal of new information on what we've been doing already, but it is useful in functions where you're working on a relative max and min in their own right, not paying attention to the first derivative test or increasing and decreasing at all. So if you have a function, and you have a critical point C, but in particular you need a place where the derivative actually has a value of 0 rather than does not exist. You also need the second derivative to exist on that place. With that notion, if you have the function being concave up at that point, it looks like this. That's a relative minimum. If you have the function being concave down, it looks like this, and that's a relative maximum. If the second derivative is 0, though, we don't get anything useful, and we do have to go back to the first derivative test.